Good afternoon. I am Shaly Singla, lecturer in physics from GPC Kundi Majra. Today my topic is Gauss's law and its applications. So, first of all, we will start with the Gauss's theorem. So, according to Gauss's law, let we have a positive charge q, let we have a positive charge q, then we have a point, given point P. So, at point P we can find the electric field due to this positive charge q. The distance between the charge q and the point P is d. So, the electric field due to this charge q at point E P is equal to q upon 4 pi epsilon naught times distance square. E is electric field. So, in vector form we can write E vector is equal to q upon 4 pi epsilon naught d square into d cap. So, this is the definition of electric field due to any point charge q at any point given point P which is located at a distance d. Epsilon naught is the absolute permittivity of free space its value is equal to 8.852 into 10 raised to power minus 12 for vacuum. So, if we have charge located in vacuum, then we have this much value. So, according to Gauss's theorem, if we have any closed surface around this given charge, then the electric flux due to this charge q, which is equal to phi, this will be equal to integral of electric field into ds vector. This is ds vector is small surface element vector. This is small surface ds of this surface S, and ds vector is perpendicular to this surface. So, if we take dot product of E vector dot ds vector and take its integral, then we get the total flux through this closed surface. So, this is equal to 1 upon epsilon naught times q. So, we can say that the total electric flux due to a positive charge q is equal to 1 upon epsilon naught times the charge itself. So, this is the definition of Gauss's theorem. The total electric flux of phi is equal to, which is equal to integral of E vector dot ds vector over the closed surface is equal to 1 upon epsilon naught times the charge q. This is charge q and the electric field is in the outward direction, and the total number of electric lines of force which is electric flux is given by this much value. This is the Gauss's theorem. Now, we will prove this theorem. proof of Gauss's law. So, to prove this theorem, first of all we will draw a diagram. This is charge q located at the center of a closed surface. The electric field, which is radially outward at any point P located on the, this is a point P located on the surface of closed surface, and let us take a small segment ds of this total surface area S. The value of ds vector is, the direction is outward. In this will be in the same direction as that of E vector. In this case, E vector is parallel to ds vector. So, firstly we will take the electric field at point P. The distance of this point P from the charge q is d. The electric field vector is equal to q upon 4 pi epsilon naught d square into d cap. D cap is a unit vector in the direction of d. So, this is expression of E vector. Then we will take Gauss's theorem, prove this theorem. So, we know that electric flux phi is equal to E vector dot S vector. S is surface area, total surface area of this closed surface. So, total flux is equal to E vector dot S vector. This can be also written as, in the integral form, E vector dot ds vector and its integral over the closed surface S. Since this surface S is divided into small surfaces ds1, ds2 and so on, when we integrate we get the total flux of through this surface S. So, putting the value of E, we have q upon 4 pi epsilon naught d square d cap dot ds vector. So, in this integral q 4 pi epsilon naught and d square, these are the constants. So, we can take these from the out from the integration. So, we have q upon 4 pi epsilon naught d square and integral of d cap dot s vector. So, then we have the flux phi is equal to q upon 4 pi epsilon naught d square into d cap dot ds vector and its integral over the closed surface. We know that d vector is, d cap is parallel to ds vector. So, this can be written as q upon 4 pi epsilon naught d square. The value of d cap is, this is a unit vector, so its value is 1, and ds, magnitude of ds vector is ds into cos of 0 degree. The angle between d cap and ds vector is 0 degree. So, this is equal to q upon 4 pi epsilon naught d square and integration over the small surface ds. When we integrate it, we have the total surface area S. So, the value of S can be written as 4 pi d square. So, in this case 4 pi and d square are cancelled out and we have flux phi is equal to q upon epsilon naught which is the statement of Gauss's law. So, hence in this way we can prove the Gauss's theorem. Now, next we come to the applications of Gauss's law. So, there are mainly two types of applications. First is deduction of Coulomb's law from Gauss's law. The second is determination of derivation of electric field due to various types of charge distributions. So, these are the two applications of this Gauss's law. In the first one we will deduce Coulomb's law, and in the second one we will derive an electric field for the various charge distributions. So, firstly we will derive Coulomb's law, derivation of Coulomb's law from Gauss's law. In this case, suppose we have a given charge q, and this is suppose source charge. Source charge means which is producing the electric field, and then we have another charge, point charge, which is q naught. This is our test charge. Test charge is that charge on which the electric field is acting. So, the direction of electric field is like this. So, firstly we will take the definition of electric field. The electric field is equal to, as we know that this is equal to force between the two charges divided by q naught. Q naught is the unit test charge. So, force per unit test charge is equal to electric field acting on the test charge. So, now we will find the value of this electric field from the Gauss's law. We know that phi is equal to E vector dot ds vector, its integration over the closed surface. This is also equal to q upon epsilon naught. Q is the source charge and epsilon naught is permittivity of free space. So, this is according to Gauss's theorem. Let us draw a Gaussian surface which is including the charge q naught, and the distance between the two charges is d. So, let us take small segment at q naught. This surface segment is ds vector. Its direction is same as in the as that of the E vector. So, we can write E vector dot ds vector is equal to integral E into ds into cos 0 degree, because the angle between E and ds is 0. So, this is equal to, since E is constant, it can be taken outside from the integration, and we have integration over the this small surface ds, which is equal to E into S, total surface area. When we integrate this small surface ds, we have total surface S, surface area of this Gaussian surface. This is Gaussian surface having surface area S. This surface area is equal to 4 pi into d square. Since this is like a sphere and its radius is d, so the surface area of this sphere is equal to 4 pi into d square. So, this is equal to q upon epsilon naught. So, when we simplify it, we have E is equal to q upon 4 pi epsilon naught into d square. So, here we have two expressions. First one is E is equal to f upon q naught. This is the first one expression, and the second expression for the electric field is q upon 4 pi epsilon naught d square. When we equate these two expressions, we have q upon 4 pi epsilon naught d square. So, from this we have the expression for the electrostatic force F between two charges q and q naught, which is equal to q into q naught divided by 4 pi epsilon naught d square. So, this is the expression for Coulomb's law. Which states that electrostatic force between two charges q and q naught is directly proportional to their product and inversely proportional to square of distance between the two charges. Hence, we have deduced Coulomb's law from the Gauss's law. Now, next is we have different types of charge distributions. The first type of charge is a simple point charge. Q. A point charge Q can be defined as a positive charge Q, which is located at a single point and which has negligible dimensions. So, this is the definition of a point charge. The second type of charge is linear charge distribution. We can distribute the charge Q in many ways. First is point charge, second one is linear charge distribution. Suppose we have a wire or a conductor and we have given it a charge Q. The length of the conductor is L. So, this positive charge gets distributed uniformly over the whole surface of this conductor or wire. So, here we have a term which is linear charge density. the charge is uniformly distributed, hence the charge at any point will be same, the charge density will be same. So, lambda is linear charge density, this is equal to total charge which is q upon the total length of the conductor which is L. So, lambda is equal to q upon L, this is linear charge density. The next type of charge distribution is surface charge distribution. In this case, suppose we have a given surface, a given sheet which is having surface area S. S is a surface area. This is a sheet. Suppose we have given a charge q to this sheet. Q is a positive charge and it is uniformly distributed over the whole surface of the sheet. So, this type of charge distribution is called surface charge distribution. Here we have surface charge density. The surface charge density is denoted by a symbol which is sigma. This is equal to total charge q upon the total surface area of the sheet S. So, sigma is equal to q upon S is surface charge density. The fourth type of distribution is volume charge distribution. In this case, we have a, suppose we have a cube. The cube has some sides, 6 sides, and it will have some volume V. This is a cube. Suppose we have distributed a charge q uniformly to this volume. So, positive charge is distributed. Here we have a term used, volume charge density. U is charge. So, the volume charge density, its symbol is rho. This is equal to total charge q upon the total volume of this cube which is V. Rho is equal to q upon V. So, these type of distributions are used to find the electric field. So, firstly we will find electric field due to a point charge. This is the second application with which we can find the electric fields due to various charges. Let us suppose we have a given point charge q which is positive charge and it is located at a given point. Now, we will find its electric field at any given point P. The point P is at a distance d from the charge q. The direction of electric field will be radially outward along the d. So, this is the direction of E. Now, we will use Gauss's theorem. According to Gauss's theorem, phi is equal to integral of E dot ds vector, which is equal to q upon epsilon naught. So, we will use this Gauss's theorem to find the electric field at this point P. So, let us construct an imaginary surface around the point P, taking Q as center. This is the center O, and P is included in the, this is called Gauss's theorem, Gaussian surface. S, its area is, surface area is S. Let us take a very small surface area ds, which is including the point P. The direction of ds vector will be, this will be also along the direction of D. So, E vector is parallel to ds vector, and the angle between E and ds is 0 degree, theta is 0 degree. So, we can write E into ds cos 0 degree is equal to q upon epsilon naught. This is integral over the closed surface, Gaussian surface S. So, E is constant, it can be taken outside from the integration sign. Here we have ds, integral of ds. This is equal to E into total surface area S. The total surface area of this sphere is 4 pi d square, which is equal to q upon epsilon naught. So, taking this 4 pi d square on the right side, in the denominator we have q upon 4 pi epsilon naught d square. So, here the expression for electric field is derived due to a point charge E is equal to q upon 4 pi epsilon naught d square. If we have to find write it in vector form, we have E vector is equal to q upon, and the direction is d cap. D cap is along this line, it is a unit vector. So, this is the first type of electric field, which is due to a point charge. The second one is electric field due to a hollow sphere or spherical shell, due to a charged hollow sphere or a spherical shell. Hollow sphere is empty from the inside. Let us draw. This is a hollow sphere. The radius of this sphere is r. So, here we have d is equal to r, and a charge q, positive charge q is given uniformly to this hollow sphere. So, this is only on the surface of this hollow sphere. And it is distributed uniformly over the whole surface. Inside the hollow sphere, the value of charge q is 0. Inside it is, since it is empty, so charge will also be 0. So, we will find the electric field due to this sphere at different points. Let us take a point on the surface. This point is P. Here we have to find the electric field. The direction of the electric field will be radially outward along the line D. Again we take a small surface area including the point P ds, and its direction is ds vector, area vector, along the